gravitational potential energy. We're going to talk, now we've done this before, right? Here's the ground. Here's an object above the ground, right? It has a mass m, and it's got a force of gravity, mg, and it's a height of y above the ground. Okay? So we say, well, what was the potential? Remember what the potential energy was for that? Or mgh, or I'm going to call it mgy, right? 'Cause y instead of h, does that bother you? It's just a variable change. mgy. And by the way, why am I doing that instead of calling it h? Because a few of you are going to take AP Physics, and we don't use h, we use y. So I'm going to do this the AP Physics way. But there's a problem. What's the gravitational potential energy? Like, let's say this is the Earth, and over here's my spacecraft, way above the Earth. What's the gravitational potential energy there? It's not mgy. Why not? Because g is not a constant anymore. What happens to the gravitational field as you get farther from the Earth's surface? It gets weaker. So, see here, we say, oh, we're so close to the Earth's surface, we're just going to use, g equals 9.8 newtons of force per kilogram of mass, right? That's the gravitational field of Earth near the Earth's surface. But as you get farther away from the Earth, g becomes different. It becomes less. So when you multiply two things together, like the gravitational field times my height, well, this thing depends on this thing now. And when that happens, you can't just multiply them together. You have to use integral calculus. And I'm going to do that now. Now, a few of you are in AMA. Is that true? Raise your hand if you're in AMA right now. Okay, what I'm going to do for you is a nice review for your final exam next week. Your calculus test. Oh, you already took it. You haven't taken a test on calculus though, have you? Oh, maybe. Never mind. Well, whatever. I'm going to do it here's what I'm going to do. Look, we have now, you don't even need to take notes for this. I just want you to watch it, okay, and see how calculus is used. It's pretty cool. But the result of doing this, you're going to have to know. Okay? Now, here's how we define potential energy. Notice something here. As this mass falls down, we lose gravitational potential energy, don't we? But gravity is doing work. Remember we said that work was equal to force times, I'm going to call it delta S. We use delta S a lot. That's a displacement, right? Force times displacement. Now, you guys have had dot products already. I know you have. You did it in AM and AMA. This is a dot product. Force is a vector, displacement's a vector. Work is the dot product of those two vectors. But now, here my force is mg. And notice something, that if gravity is doing positive work, I'm losing potential energy. See, look, if the force of gravity is down and my delta S, my displacement is down, the force and displacement are in the same direction, and therefore gravity is doing positive work. But as gravity does positive work, I'm losing gravitational potential energy. And it turns out that this is true. The change in gravitational potential energy is going to be equal to the negative work done by gravity. Okay? So, now, what integral calculus is, it's when, it's what you use when you're trying to multiply two quantities together, but where one quantity depends on the other quantity. Okay? If the force is a constant, you don't need to use integral calculus. You just go force times displacement, and you got it. But if your force of gravity depends on what your position is, if it depends on S, well, you're in trouble. Well, you're not in trouble if you know how to use calculus. Oh, I made a mistake here, didn't I? It's not delta S anymore, is it? Some of you might know. what we do is we call this, instead of delta S, we call it ds. ds. All right. So this is what we're going to use. It's an integral. And now I need a better description for gravity. The force of gravity is a vector. And here's our force of gravity, right? Straight down. Force of gravity is equal to GMM over r squared. But it's a vector. We need to describe its direction. And here's how we do it. And you may have never have seen this before, and if this confuses you, don't worry about it. Okay, just soak it in. We use these things called unit vectors. They're little things that allow us to say, hey, it's in this direction. This stuff is in this direction. Well, we have a vector called r hat. And r hat means away from the center of a circle. Literally, that's what it means. If you see r hat, that means, okay, what's the direction? The direction is away from the center of the circle. But gravity is not away from the center of a circle. It's towards the center of a circle, isn't it? So what's the opposite of r hat? That would be good. No, we call it negative r hat. It's in the opposite direction. Remember the vectors? You multiply them by -1 and you get the opposite direction. So here's the magnitude of the force of gravity. But this means, hey, gravity, it falls down. Okay, does that freak you out? This is a fancy way of saying down. R hat means up. Negative R hat means down. So don't be freaked out by that. All right, so now I'm going to put this in here and say, okay, delta U is equal to negative the integral of GMM over r squared in the negative r hat direction, dotted with ds. Now ds is a little tiny displacement vector, but what the dot product means is, hey, only the part of your displacement that's changing r, or your distance away from the center, matters. So we don't really care about delta s. What we're going to care about is delta r, our change in r, or dr in the r hat direction. Now, if that confuses you, again, in AP, those of you taking AP Physics, or if you're going to go on and take calculus-based physics in college, you'll go over this. I'm blowing through this really fast because I want to get to its result. The thing is, I don't want you to just throw an equation out there and not show you where it came from. Okay? So now we have r hat dot r hat. Well, r hat dot r hat turns out to be 1. Anytime you take the dot product of the same unit vector, you get an answer of 1. So that goes away. We have the negative here, and so delta U is equal to this negative cancels this negative. We're going to go from r initial to r final. We are doing a definite integral here. A definite integral, definitely using integration here. GMM over r squared dr. Now this looks really scary, but G and M, those are the masses, and G, those are constants. They don't change with R. So I'm going to pull them out of the integral. Now, what is a way of saying 1 over r squared? How about r to the negative 2 power? Does that help? Does that make sense? Times dr. Now, all of you that have taken AMA, you know how to do this. R to the negative 2 times dr. If it's confusing, just put an x in there instead of an r. It doesn't matter. What is x to the negative 2 dx? What's the integral of that? What rule do you use? The power rule for integration. Remember the power rule? Okay, what do you do to this exponent? Huh? You add 1 to it. You're thinking of derivatives. Derivatives, you take 1 down. But integrals, just the opposite. You add 1 to it. So what is negative 2 plus 1? Negative 1? Yeah. Negative 2 plus 1 is negative 1, people. All right, so that's going to be negative 1. So what we're going to get is delta U, is equal to GMM. And then we're going to have a negative 1 over r. Okay, that's the integral of this. Because We got r to the negative 1. What is r to the negative 1? It's 1 over r. And then we have then you divide by the new exponent. Remember that in the power rule? You divide by the new exponent. Well, what's the new exponent? Negative 1. So I put it right there. Then we're going to evaluate it from r initial to r final. Okay, so I'm just going to plug these finals and initials in there, put the negative out here, negative GMM, and this is going to be 1 over r final minus 1 over r initial. Okay. Now, this part might seem a little bit confusing, but it's all right. When you have a definition for what potential energy is, you have to define a reference. What place in the universe are you going to measure gravitational potential energy from? When we did this, where do we measure potential energy from? From the ground. And y was our height above the ground. So we had to say, hey, we're going to measure the potential energy from the ground. Here we're going to pick a very weird place to measure gravitational potential energy from. We're going to measure potential energy from infinity. I love Toy Story, right? Infinity and beyond, okay? That's where we're going to measure gravitation. We're going to say this. Let r initial go to infinity. All right? So, okay, here's my planet. And I'm going to say, if I go really far away, billions and billions of miles, well, more than that because it's infinity, I'm going to call that 0. Now, why would I call that 0? This is very convenient. Look at this. What is 1 over something that's going to infinity? No. If I divide by a hugely large number, what do I get? Huh? Not half. What? You get 0. You get nothing. If I divided you into an infinitely small number of pieces right now, how big would those pieces be? They'd be 0. An infinitely number of pieces, I'd even have to divide your atoms in half, crying out loud. So this, if we let r initial go to 0, or if we let r initial go to infinity, that means that 1 over r initial will go to 0. That means this will go to 0. This is very convenient. I'm dealing with a delta U here. Delta U equals U final minus U initial. So if we let R initial equal infinity, and then if we let R final, we're just going to say it's equal to R. R is my distance away from the center of the planet. This goes to 0, and U final, well, so this U final is, we're just going to call it U. Our potential energy is equal to, well, put an R right there, negative GMM over R. Now, and this is my equation for gravitational potential energy. Okay? It's weird. And look, I had to do all this fancy mathematics that's, for the vast majority of you, beyond where you are right now. Okay? Don't worry. I mean, you're doing math way beyond what freshmen in high school, do in a couple of years. For many of you, if you go on and study, math and science, engineering, what you do now will seem easy compared to what you're doing then. Actually, you guys are only typically about a year and a half in math from doing what I just did. If you take Calc AB or Calc BC next year, you'll be doing this. It'll be very straightforward. Okay. So to summarize, let me just do it right here. What did we talk about so far today? Well, we know that the force of gravity is equal to GMM over R squared. And I'll go ahead in the negative R hat direction. What does that negative R hat direction mean? Down. It means down. That's a fancy way of saying down. That's all. It doesn't add any value or anything. And we also learned that using that the orbital velocity equation is equal to g m m over r. Oh, wait. Oh, no, I'm being stupid. Hold on. Need an eraser. Erase it all. Oh, I hate being human sometimes. All right. Most of the time it's pretty cool. It's the square root of gm over r. Okay? And we also learned that, hey, the way we're going to measure potential energy in space is equal to negative gmm over r. Now make sure you know what all these mean. Okay? This is the mass of my spacecraft, little m. This is the mass of the planet, like Earth or Mars or the Moon. This is big G. And r is my distance away from the center of that planet, the Earth or the Moon. Okay? We have one more equation to derive. The escape velocity equation. But we're going to do that tomorrow.